Imagine standing on a world where the sunset isn't golden but blue, where the sky glows a dusty pink, and the horizon stretches into a vast, barren wilderness. Welcome to Mars. Known as the fourth planet from the Sun, Mars bears the moniker of the Red Planet, a name as evocative as the planet itself. But why red? This characteristic hue comes from iron oxide, or rust, that pervades its surface, painting the planet in shades of ochre and crimson. Mars orbits our Sun at an average distance of about 141 million miles. Smaller than Earth, its barren landscapes are swept by dust storms and peppered with both vast flat plains and some of the solar system's tallest volcanoes. The planet's striking appearance and mysterious nature have captivated human interest for centuries, inspiring countless missions to uncover its secrets. Now, let's delve deeper into what makes Mars a captivating subject of study and exploration. Mars boasts the tallest volcano and the deepest, longest canyon in our solar system. Welcome to the rugged terrain of Mars, a world of extremes where the landscapes are as magnificent as they are mysterious. At the heart of these Martian wonders is Olympus Mons, a colossal shield volcano that stands nearly 3 times the height of Mount Everest. This giant, stretching 22 kilometers into the Martian sky, is not just the tallest volcano on Mars, it's the tallest in the entire solar system. The base of Olympus Mons is approximately the size of the state of New Mexico, making it a behemoth that dominates the Martian landscape. Moving from the heights of volcanic peaks to the depths of canyons, let's explore Valles Marineris. This vast canyon system on Mars is not just a simple ditch, it's a complex, sprawling network of valleys that extends over 4,000 kilometers, making it close to 10 times longer than the Grand Canyon. With depths reaching up to 7 kilometers, Valles Marineris is a monumental rift in the Martian crust that could hide the entire Mount Everest within its depths. Aside from these giants, Mars also hosts polar ice caps at both its poles. These are not just ordinary ice caps, they are composed of layers of water ice and carbon dioxide ice, or dry ice. During the Martian winter, the temperature is cold enough to freeze the carbon dioxide out of the atmosphere, adding to the polar cap's mass. These caps are dynamic, waxing and waning with the seasons, a process that dramatically influences Mars's climate and atmosphere. These dramatic landscapes not only reveal Mars' dynamic history but also hint at its mysteries beneath the surface. Breathing on Mars? That's a challenge, with an atmosphere about 100 times thinner than Earth's. Picture standing atop a high mountain, gasping in the thin air, but multiply that feeling manifold, a situation not for the faint-hearted or the unprepared. Let's delve into the composition of this sparse Martian veil. Dominantly, the atmosphere is composed of carbon dioxide, making up about 95% of it. Nitrogen and argon follow, albeit in much smaller quantities. This composition starkly contrasts with Earth's life-supporting mix, rich in oxygen and protective layers that shield us from solar and cosmic radiation. The thinness of Mars's atmosphere brings about extreme temperature fluctuations. Daytime might feel like an autumn day in the desert, but when the sun sets, temperatures plummet dramatically, often reaching lows that would make Antarctic winters seem mild. This severe temperature variance is a direct consequence of the atmosphere's inability to retain heat. Moreover, the Martian sky, rather than the familiar blue, presents a butterscotch hue during the day. This is due to fine dust particles suspended in the atmosphere, scattering the incoming sunlight. At sunset, these particles help scatter the light in a way that swathes the sky in shades of blue, a reverse of our own earthly experiences. Radiation protection, or the lack thereof, is another critical issue. Without a substantial atmosphere or a magnetic field, Mars offers no shield against harmful cosmic rays and solar radiation. This poses significant challenges for any potential human visitors or settlers, who must find innovative ways to protect themselves, possibly through underground habitats or heavily shielded structures. The implications for future colonization are profound. Every aspect of daily life would need to be re-engineered. Habitation modules would need to be not only airtight but also capable of withstanding great temperature extremes and radiation exposure. Generating breathable air and maintaining suitable living temperatures would require sophisticated life support systems and technologies. Understanding Mars's atmosphere is key to unlocking the secrets of daily survival on this alien world. As we continue to study and explore, each piece of data helps us piece together the puzzle of how humans might one day live and thrive on the Red Planet. Could Mars be a home for life, or has it ever been? The quest to find this answer fuels countless missions. The fascination with Mars and the possibility of life there has a long history, sparked by early telescopic observations and growing more intense with each passing decade. The journey began in earnest in the mid-20th century when humanity first sent spacecraft to study the planet up close. One of the landmark missions in this quest was NASA's Viking program in the mid-1970s. Viking 1 and Viking 2 were the first spacecraft to land successfully on Mars and conduct experiments specifically designed to detect life. They tested Martian soil for biological activity and, intriguingly, some of their results were ambiguous. While no clear evidence of life was found, the experiments opened more questions than they answered, fueling further scientific inquiry. Fast forward to 1997, and the Mars Pathfinder mission took a different approach. Alongside its lander, it deployed Sojourner, a small rover that roamed the Martian surface. Its primary role wasn't to search for life directly, but to analyze the geology of Mars. Understanding the planet's geological context is crucial because it sets the stage for understanding how and where life could potentially exist. In the 2000s, the Mars exploration rovers, Spirit and Opportunity, took up the mantle. These rovers were equipped with tools to grind into rocks and analyze their compositions, looking for signs of past water activity. Why water? Because on Earth, where there's water, there's life. The discoveries of these rovers pushed our understanding further, finding evidence of ancient water flows and possibly habitable conditions in Mars's distant past. More recently, the focus has shifted beneath the surface. The discovery of underground ice reserves and the seasonal spikes of methane in the Martian atmosphere suggest active processes that could potentially support life. Methane is particularly exciting because on Earth it's often produced biologically. Could Martian methane also be a sign of life? The answer isn't clear yet, but it's a tantalizing possibility. The role of rovers continues to be pivotal in this ongoing quest. These robotic explorers analyze soil samples, drill into rocks, and even look for organic compounds, the chemical building blocks of life. Each rover mission is more advanced than the last, equipped with better tools and technology to delve deeper into the Martian mystery. The search for life on Mars is a patchwork of missions, each adding a piece to the larger puzzle. It's a story of technological triumph and scientific curiosity, of pushing boundaries and challenging what we know about life itself. While definitive proof remains elusive, the pieces of the puzzle about life on Mars are slowly coming together. Humans setting foot on Mars isn't a question of if, but when. The red soil of Mars may soon bear the footprints of the first human explorers, marking a monumental milestone in our history. The plans to send humans to Mars are ambitious and are being spearheaded by both national space agencies and private entities like SpaceX. NASA's Artemis program, aiming to return humans to the Moon, is just a precursor to the eventual manned missions to Mars, potentially in the late 2030s. Meanwhile, SpaceX, with its Starship spacecraft, proposes an even more aggressive timeline, hoping to land humans on Mars within this decade. The challenges of sending humans to Mars are, without exaggeration, colossal. One of the primary concerns is the journey itself, which could take anywhere from 6 to 9 months, depending on the alignment of the planets. This long-duration spaceflight presents numerous hazards, including exposure to cosmic radiation and the psychological impacts of prolonged isolation. Moreover, once on Mars, humans will have to contend with a hostile environment. The Martian atmosphere, composed mostly of carbon dioxide, offers no breathable air, and the planet's surface is bombarded with radiation due to its thin atmosphere. Technologies to mitigate these dangers are under development, such as radiation shields and systems to produce water and oxygen from local resources. But why go through all this trouble? Mars serves not only as a new frontier for human exploration, but also as a potential stepping stone for deeper space exploration. Establishing a sustainable human presence on Mars could pave the way for missions to more distant worlds, acting as a laboratory for testing life support technologies and strategies for living off-planet. Innovations required for these missions are not merely incremental. We're talking about advances in propulsion technology, life support systems, and sustainable habitats. These developments could also drive improvements in similar systems back on Earth, demonstrating the dual benefits of space exploration. The journey to Mars extends beyond mere travel. It represents the next giant leap for mankind.